Hey, this is Allie, and I'm gonna step us through this problem from class about unidirectional conduction in a slab when the thermal conductivity is not constant. So we'll start by drawing out the geometry of this problem. We have a 1 meter thick wall, and the boundary condition on this end is that it's in a furnace, so it's 450 centigrade. And the boundary condition on this end is that it's 25 centigrade. And I'll say this is x equals 0, and this is x equals 1 meter. And the coordinates that you choose are arbitrary. I've chosen this so that Q is positive in this case. The question is asking for the position in the wall at which the temperature is 127 degrees. So at some x position, x unknown, we have T equal to 127 degrees C. Okay, so what we need to know to solve this question is the temperature profile. Temperature is a function of x. And whenever we have a heat transfer problem requesting a temperature profile, we use a governing differential equation based on conservation of energy, rather than just using Fourier's law, which is a constitutive equation. And so the correct governing differential equation here is the one that we derived in class, and we're not making the assumption that K is constant, so we're not taking it out of that first differential. This is a second order differential equation because there's two derivatives here. So we're going to need two boundary conditions to solve this. And those are given in the problem statement. At x equals 0, the temperature is 450 degrees C. And we're going to convert that to Kelvin because we notice up here that the constants A and B are given in units of Kelvin, and so to avoid making a mistake, it's easier to just convert our temperatures to Kelvin. So that's 723. And then our second boundary condition is at that x equals 1 meter point where the temperature is ambient. Okay, to solve this differential equation, it's separable, so we will just separate and start integrating. And the first integration, the left-hand side is 0, but we do have a constant of integration, C1. And the right-hand side just returns the argument of this derivative. Okay, now we can differentiate again. Integrate again. The left-hand side, the integral of C1 is C1x. There's a second constant of integration. And then to crack this right-hand side, we have to insert the dependence of K upon T. And integrating that expression, gives us our actual temperature profile. And so this is the mathematical form of the temperature profile. And I'm going to call this the real temperature profile. And it's real in as much as we have used the most accurate value of K possible. At this point, we were given the constants A and B, and we need to solve for the constants C1 and C2. And to do that, we'll use the boundary conditions. So we'll start with the boundary condition that has a 0, because usually those reduce the complexity of a problem the most quickly. Not always, but it's a good stab. And this is true at 723 Kelvin. And as promised, we lose our C1 term. So, sorry, that's an equals. There we go. So at this point, we can solve directly for C2 because we have values for A and B that are given up here. They're constants. And so if we go ahead and just compute that, we get C1. And once we know C1, we can plug that back into the equation with our second boundary condition at 1 meter. And this is for a temperature of 298 Kelvin. And when we do that, we're able to solve for C2. So now we know every single constant in the real temperature profile. And so that's fully mathematically solved. We could write it in terms of the constants, but then it just gets a little bit messy. But the question wasn't asking for the temperature profile. It was asking for the x value at which the temperature is equal to 127. So let's take our temperature profile, and we want to know T127, and in Kelvin, that's going to be 400 Kelvin. So we'll plug 400 Kelvin into our temperature profile and compute the x that corresponds to that. And this is just doing the algebra to solve for that x. We'll call that x 400K. And we know all these constants, and if we compute the value of x, we get 0.889 meters. And so that is the true position in the wall where the temperature is 127 C, 400K. Awesome. However, the question also asks us, what if we had made the assumption that K was constant? And if we had made that assumption, we wouldn't have done the integration up here with this dependence. So instead, we would have had C1 times x plus C2 equals the integral of kt, where k is constant, it's dt, equals kt. Actually, I'm going to make this C1 prime and C2 prime because those values are different from the values that we computed above. Okay, so again, we can use the same boundary conditions as here because the boundary conditions haven't changed. It's just that our constants of integration are changing because we've changed the form of the equation we're using. If we do that, we do get a significant difference in the values of C1 and C2. So at this point, we can solve the temperature profile. We'll choose the temperature 400 again. And this will give us the value of x 400K prime. And that prime means that we're making the assumption that K is constant. And that value, that spatial position, is 0.76 meters. So this is the real position, and this is the position with an assumption. And that assumption was that K was constant. Okay, so that's two parts of the question. There's one more part, and that's, let's say we actually went ahead and used this assumption and we put our pipe in at this position. And so this is going to be us putting it in somewhere over here. This is not to scale. It's not going to be at the temperature we expect it to be. So what temperature are we actually going to be at if we put our pipe at this position? All right, so we'll move on to a new page, and we'll say, okay, the same temperature profile applies, and that is the true temperature profile, the real temperature profile, because that's what's really happening in the world as best we can model it. But what we fail to do is accurately calculate our position. So in this case, we're using the position that's not quite right. We'll plug that in and we'll calculate T. So we have A over 2 and what I've done here is rewrite this in the standard form for a quadratic equation, because that's what this is. In order to solve for the temperature, we're going to get two values because, well, it's parabolic. So that just requires us recalling the quadratic equation, which if it's been a while, that could be slightly challenging. That's what Wikipedia is for, right? This is something that I would certainly give you on the exam, the quadratic equation, if you needed it. And so here we have A is, B is just B, and C is negative. And if we plug in those values, we get two values for T. The first one is 473. Oops. And the second is a negative value. Going back to the geometry of the problem, these are positive temperatures on both ends, so we can pretty much discount the negative solution. And the true solution is 473. So if we were to put this pipe in, making an approximation for the thermal conductivity being constant, we would aim to have a temperature of 400 K, and we would actually get a temperature of 473 K. So you can imagine that amount of superheating could actually cause a lot of damage to the pipes because you would have a much greater pressure duty than you expect. So this example basically showed us why it's important to consider the temperature dependence of thermal conductivity and how we can do that by just choosing the correct form of the governing differential equation here. All right, thank you so much.